The hyperbolic functions, in some cases with proper domain restrictions, can be expressed as one-to-one functions and therefore have inverses, and that's what we're going to look at now. Consider y equals the inverse hyperbolic cosine of x. It's a lot of symbols, it's a lot of words. Well, y equals the inverse hyperbolic cosine of x if and only if x is equal to the hyperbolic cosine of y, which would mean that by definition of hyperbolic cosine, x is equal to e to the y plus e to the negative y over 2. And our goal at this point will be to solve for y. Solving for y will give us an expression for the inverse hyperbolic cosine of x. First, I'm going to clear the fraction, and so I have 2x is equal to e to the y plus e to the negative y. Gathering together everything non-zero on one side of the equation, we end up with e to the y minus 2x plus e to the negative y is equal to 0. The e to the negative y, of course, represents 1 over e to the y, and so clearing that fraction requires us to multiply both sides by e to the y. And by so doing, we end up with e to the 2y minus 2x e to the y plus 1 is equal to 0. This looks fairly hideous, but it is quadratic in e to the y. So to express that, I'm going to rewrite e to the 2y as e to the y squared. And then I'll rewrite everything else. Minus 2x e to the y plus 1 is equal to 0. Now we can see I have thing squared minus 2x thing plus 1 equals 0. And that fits the form of a quadratic. Now we may want to gravitate to x, but remembering we're trying to solve for y indicates that I want to set e to the y equal to an expression we get from the quadratic formula. And so e to the y is equal to 2x plus or minus the square root of 4x squared minus 4 all over 2, where our coefficients are 1, negative 2x, and 1. Simplifying the square root allows us to say the e to the y, and then reducing the fraction, is equal to x plus or minus the square root of x squared minus 1. Now we're not done yet because we haven't solved for y. We have e to the y equals a bunch of stuff, but we do need to deal with the fact that we have this plus minus here. And actually, we don't have to deal with it. The math folks have dealt with it. They have said we're going to consider only the plus by convention. And by doing that, we can express y as a function. By applying the natural log to both sides, we get that y is equal to the natural log of the quantity of x plus the square root of x squared minus 1. And if you recall, when we started this whole mess, y was equal to the inverse hyperbolic cosine of x. Therefore, we have an expression for the inverse hyperbolic cosine of x. It's the natural log of the quantity of x plus the square root of x squared minus 1. Our author makes a note that it makes sense that since the hyperbolic functions are defined in terms of exponentials, that their inverses would be defined in terms of a natural logarithm. And here we have some information from our textbook. We can similarly derive the inverse hyperbolic sine of x. It is the natural log of the quantity of 1 plus x squared plus 1. Notice because of where the x's appear, like x squared plus 1 inside of a square root, for the inverse hyperbolic sine, x can be any real number. However, for the inverse hyperbolic cosine, we have x squared minus 1 inside of a square root. Therefore, x has to be greater than or equal to 1. And likewise, a similar process to what we just saw would give you that the inverse hyperbolic tangent of x is 1/2 natural log of 1 plus x divided by 1 minus x, where x is between negative 1 and 1. And you'll see that these domain restrictions on the inverse functions actually match up perfectly, as they should, with the ranges of the original hyperbolic functions. As for differentiating these, for y equals the inverse hyperbolic cosine of x, we would use the definition, the natural log of x plus the square root of x squared minus 1. Y prime would equal 1 over the square root of x squared minus 1. We actually saw this in a previous video on derivatives of natural or logarithmic functions. And just by powering through using our rules of differentiation and the definitions that we have here derivatives of inverse hyperbolic functions. So the inverse hyperbolic sine has a derivative that is 1 over the square root of 1 plus x squared. The inverse hyperbolic tangent has a derivative of 1 over 1 minus x squared. And that actually matches what you see for the inverse hyperbolic cotangent, but there's this note over here where we see that the domains of the inverse hyperbolic cotangent and the inverse hyperbolic tangent don't have any numbers in common. They're defined for different x values or different input values. The inverse hyperbolic tangent is only defined when the absolute value of x is less than 1, and for the inverse hyperbolic cotangent, absolute value of x has to be greater than 1. I don't require anybody to memorize these formulas at all. I just want you to know that they exist and be able to use them if they show up in any of our work. Just as we saw that the hyperbolic functions show up here and there, like a catenary and in the St. Louis Arch, in the case of a boat approaching a dock, I know, that came out of nowhere, right? Suppose you're on the boat and you throw a rope to somebody who is standing on the dock. So here goes the rope, and the person catches it, and then the person starts walking along the dock. The boat will follow a curved path that eventually lands you next to the dock, parallel to it. Apparently in the picture that I've drawn, though, our individual carrying the rope will fall off of the dock, but that's not the point. The point is this curve here. If A is the distance between the boat and the dock, the initial distance, if we imagine x and y axes that follow the path of the boat and the person walking along the dock, then the path of the boat can be described by an equation. Y equals a times the inverse hyperbolic secant of x over a minus the square root of a squared minus x squared. I will not ask you to work with this equation. I'm not going to develop it or anything, but I just want you to know that the path that the boat travels is described by one of these inverse hyperbolic functions. One example to conclude this video here, the integral from 0 to 1 of 1 over the square root of 16t squared plus 1 dt. The instructions here are to evaluate the integral. Well, folks, if we were looking at the integral of 1 over 16t squared plus 1 dt, then I would be looking at an inverse tangent function. But that's not what we have. We have a square root in the denominator, and we have some differentiation rules that might help us out here. Looking at the derivatives of the inverse hyperbolic functions, I see that one of them has 1 over the square root of 1 plus x squared. So that actually fits the form of what we're looking at here with our integral. We do have to use a u substitution here. It doesn't have to be a u substitution, but we're going to use a substitution here. U is equal to 16, no. U is going to be 4t because our radicand is really, I'm envisioning this as a u squared plus 1. Because here, for the inverse hyperbolic sine function, its derivative is the square root of, 1 over the square root of 1 plus x squared. So this x squared is going to be represented by a u squared. Therefore, u has to equal 4t. So du is 4 dt, and we're going to multiply and divide by 4. So we end up with 1/4 times the inverse hyperbolic sine, because that's the pattern that we met up with over here with the derivatives of u, but u is 4t. And that will be evaluated from 0 to 1. But then how do we do that? We go to the logarithmic definition of the inverse hyperbolic sine function, which is natural log of argument plus the square root of argument squared plus 1. And so 1/4 times the natural log of the quantity of 4x plus the square root of 16t squared plus 1. Oh dear. I said 4x and I meant 4t, didn't I? There we go. And we're going to evaluate that from 0 to 1. You can confirm that our result will be 1/4 times the natural log of the quantity of 4 plus the square root of 17. You may want to pull that 1/4 as an exponent, make it a fourth root. If you want to do that, go right ahead. I'm happy with this form of an answer.